A diode is a one-way valve for electric current. It lets current pass easily in one direction. It blocks current in the other direction. That single behavior is the subject of this lesson. Look at the current voltage curve. In one direction, current rises sharply once the voltage is high enough. In the other direction, current stays near zero. We call the easy direction forward and the block direction reverse. This device is built from one structure called a p-n junction. The symbol is just two regions of silicon joined together. One region is p-type. The other is n-type. So the lesson answers one question. Why does a piece of silicon behave like a one-way valve? Everything that follows builds that answer in order. The p-n junction is the building block of modern electronics. Every rectifier uses it. Every LED uses it. Every solar cell uses it. Two junctions placed back-to-back form a transistor. Learn this one structure, and you have the foundation for all of them. To explain the junction, we first need the material it is made from. Next, we examine the semiconductor itself. A semiconductor is a material whose conductivity we control by adding impurities. Pure silicon conducts poorly. We change that by doping it. Doping means adding a small number of foreign atoms. Donor atoms add free electrons and make n-type material. Acceptor atoms add free holes and make p-type material. Electrons carry negative charge, and holes act as positive carriers. In n-type material, electrons are the majority carriers. In p-type material, holes are the majority carriers. Each type also holds a small number of the opposite carrier, called minority carriers. The two populations are linked by a fixed relationship. This is the mass-action law. The product of electron concentration and hole concentration is constant at a fixed temperature. That constant is the square of the intrinsic concentration, Ni. For silicon at 300 Kelvin, Ni is about 1.0 to 1.5 times 10 to the 10th per cubic centimeter. This number turns the word tiny into an actual value. In n-type material, the electron concentration equals the donor density, Nd. The minority hole concentration is Ni squared divided by Nd. The same logic applies to p-type material with the acceptor density, Na. Because the doping densities are large, the minority population is extremely small. One point must be clear before we continue. At room temperature, the dopants are already fully ionized. Donors have given up their extra electron. Acceptors have already captured one. This is true before any junction is formed. A uniformly doped bar of silicon is not yet interesting. It has no built-in field, so it behaves like a resistor. The useful physics begins only when we join to different regions. So what happens when p-type and n-type silicon meet? This leads directly to the junction. A p-n junction forms where p-type and n-type material meet in one crystal. The two sides start with very different carrier concentrations. That difference sets everything in motion. Two transport mechanisms act at the junction. Diffusion moves majority carriers down their concentration gradient, from high concentration to low. Drift moves carriers under the force of an electric field. These two mechanisms compete. When the junction forms, electrons diffuse from the n side and holes diffuse from the p side. They cross the boundary and recombine. This leaves a thin region with no mobile carriers. We must be precise about what remains. The leftover charges are the fixed, already ionized dopant ions. Positive donor ions sit on the n side. Negative acceptor ions sit on the p side. These ions were always ionized. Diffusion simply uncovered them by removing the mobile carriers that had hidden them. This carrier-free zone is the depletion region. We also call it the space charge region, or SCR. The neutral material on either side is the quasi-neutral region, or QNR. We will need both terms again later. The uncovered ions carry charge, and separated charge creates a field. Now consider what that field does. The exposed ions set up an electric field across the depletion region. The field points from the positive n-side ions toward the negative p-side ions. It opposes further diffusion of majority carriers. That field corresponds to a voltage step across the junction. We call this the built-in potential. It is the equilibrium barrier that majority carriers must climb. This equation gives the built-in potential, VBI. It depends on the two doping densities and on Ni squared. The term kT over Q is the thermal voltage, written VT. At 300 Kelvin, the thermal voltage is about 25.85 millivolts. It sets the natural voltage scale for everything inside the junction. For typical silicon doping, The built-in potential is about 0.6 to 0.9 volts. It grows as doping increases. Germanium is lower because its intrinsic concentration is larger. Here is the most important clarification in this lesson. Three different quantities are often blurred into one number, 0.7 volts. Keep them separate. The first is the built-in potential, VBI. It is the equilibrium band bending set by doping. You cannot read it on a voltmeter because the contacts add potentials that cancel it. The second is the forward turn-on voltage, the NI. It is about 0.7 volts for silicon and about 0.3 volts for germanium. This is a practical value where the current becomes large. It is not equal to VBI, and it is not a hard threshold. The third is the barrier seen by the majority carriers. Forward bias lowers this barrier. Reverse bias raises it. The silicon to germanium gap comes from their different intrinsic concentrations, not from arbitrary constants. At zero bias, drift and diffusion cancel exactly, so the net current is zero. The barrier holds the carriers in balance. We have described this balance with positions and fields. The same balance can be drawn a second way. Now consider the energy band view. The energy band view describes the same junction using electron energy instead of position. It tracks two bands and one reference level. The conduction band holds free electrons. The valence band holds holes. The Fermi level marks the equilibrium energy. In equilibrium, the Fermi level is flat across the whole junction. The bands bend to make this happen. The amount of bending equals Q times VBI. That statement connects the two pictures. The band step you see is the built-in potential, drawn as energy. The barrier height is literally this step. That is a cleaner idea than calling it a resistance of the depletion region. Forward bias reduces the band step. With a smaller step, more carriers have enough energy to cross. This is why forward current grows. Reverse bias increases the band step. With a larger step, almost no majority carriers cross. This is why reverse current stays small. One detail belongs here as an optional aside. Under bias, the single Fermi level splits into two quasi-Fermi levels. Their separation equals the applied voltage. This is the same physics as the previous two beats, not a new phenomenon. We have only changed the drawing from position to energy. With both pictures in hand, we can apply an external voltage on purpose. Next we examine biasing. Biasing means applying an external voltage across the junction. That voltage adds to or opposes the built-in field. The result changes both the depletion width and the current. Forward bias pushes majority carriers toward the junction. It partly cancels the built-in field and narrows the depletion region. Carriers then cross more easily, and current rises. Reverse bias pulls majority carriers away from the junction. It reinforces the built-in field and widens the depletion region. The majority current is suppressed. This equation gives the depletion width W. It depends on the built-in potential minus the applied voltage, and on the doping. When 5 is positive, the width shrinks. When V is negative, the width grows. This is the diode equation. Current depends exponentially on the applied voltage divided by the thermal voltage. Is is the saturation current, and N is the ideality factor, between 1 and 2. One misconception must be corrected here. The diode conducts at all forward voltages, because the relationship is exponential. The value 0.7 volts is simply where the steep part lands on a linear plot. It is not a switch that turns on at a fixed point. The depletion width changed with bias, and a changing width has a second consequence. This leads directly to capacitance. The depletion region stores charge, so the junction also behaves as a capacitor. Two ion layers of opposite signs sit across an insulating gap. That is the structure of a capacitor. This gives the junction capacitance, Cj. It depends on the permittivity, the junction area, and the depletion width W. Because reverse bias widens W, the capacitance falls as reverse voltage rises. That dependence has a direct use. The junction becomes a voltage-controlled capacitor, tuned by the reverse voltage. This is exactly how a varactor tunes radio and RF circuits. There are two capacitances, and they must not be conflated. Junction capacitance dominates under reverse bias. Diffusion capacitance from stored minority charge dominates under forward bias. Stored charge also limits speed. To turn a conducting diode off, the stored minority charge must first be swept out. This delay is the reverse recovery time, and it limits how fast a diode can switch. Fast diodes and Schottky diodes exist to reduce it. Notice that one mechanism produced two consequences. The same widening depletion region that blocks DC current also shrinks the capacitance. We have covered forward behavior and capacitance. Now we examine the small current that flows under reverse bias. Under reverse bias, a small and nearly constant current still flows. It is carried by minority carriers crossing the junction. We call it the reverse saturation current, IS. The current saturates because the minority population is limited. The field sweeps these carriers across quickly, but it cannot create more of them. So the current levels off and, in the ideal case, does not grow with voltage. This equation gives the ideal saturation current. The minority concentrations P0 and P0 both contain an I squared. The result is that IS is proportional to an I squared. That proportionality makes IS strongly temperature dependent. The intrinsic concentration squared grows with temperature through this expression. The exponential factor with the bandgap Eg drives most of the change. In magnitude, the reverse current is tiny, in the microamp to nanoamp range. A common rule of thumb says IS doubles for every 10 degrees Celsius. For silicon, the real doubling interval is closer to 8 to 10 degrees. Treat it as a rule of thumb, not a law. The same thermal scale appears in the forward direction. At 300 Kelvin, the forward current rises 1 decade for about every 59.5 millivolts. That value is 2.3 times the thermal voltage. One real-world nuance is worth stating. In actual silicon diodes, the measured reverse current is usually dominated by generation recombination current in the depletion region. That current scales as an I, not an I squared, and it creeps up slowly as reverse voltage widens W. The perfectly flat reverse current is the ideal picture. Real reverse current rises a little. The reverse current stays small only up to a limit. Past a certain reverse voltage, the behavior changes sharply. Next, we examine breakdown. Breakdown is the sharp rise in reverse current past a certain reverse voltage. Below this voltage, the diode blocks. Above it, current increases rapidly. Two distinct mechanisms cause it. The first mechanism is Zener breakdown. It comes from band-to-band tunneling across a thin depletion region. It dominates at low breakdown voltages, below about 5 to 6 volts, in heavily doped junctions. Its temperature coefficient is negative. The second mechanism is avalanche breakdown. Here carriers gain enough energy to knock loose more carriers, a process called impact ionization. The current surge comes from this multiplication, which creates new electron-hole pairs. Avalanche dominates above about 6 to 7 volts, and its temperature coefficient is positive. Naming both mechanisms, with their opposite temperature coefficients, is the key engineering distinction. The avalanche surge is new carriers being created, not just existing minority carriers being swept across. Breakdown is non-destructive if the current is limited. The junction survives as long as the external circuit caps the current. This controlled breakdown is exactly how a Zener voltage reference works. We have now described the full current voltage behavior, forward and reverse. The last step is to see where this one structure is used. This leads directly to applications. One PN junction supports many different jobs. Each application uses the same structure in a different regime. We will take them in turn. The first job is rectification. The one-way behavior converts alternating current into direct current. Half-wave and full-wave bridge circuits use this. It is the most common diode job, and the reason power adapters exist. The second job is light emission. A forward bias junction drives electrons and holes together, and recombination releases the energy as light. The photon energy is roughly equal to the bandgap, so the material sets the color of the LED. The third job is energy capture. A solar cell runs the process in reverse. Light creates electron-hole pairs inside the junction, and the built-in field separates them into current. It is, in short, a diode operated in the light. The fourth job is amplification and switching. A bipolar transistor is to PN junctions placed back to back. Everything in this lesson is therefore the foundation of amplifiers and logic. A fifth job reuses the breakdown region. A Zener reference holds a stable voltage by operating in controlled breakdown. The mechanism from the previous beat becomes a design tool. This is the unifying idea. One junction, many jobs. Forward for LEDs. Illuminated and reverse for solar cells. Periodic switching for rectifiers. Breakdown for Zeners. We can now answer the opening question. A piece of silicon behaves like a one-way valve because a p-n junction builds an internal field that allows current one way and opposes it the other. From that single mechanism, the entire family of devices follows.